In the last video, we talked about distance, displacement, average velocity, and we talked about average speed. Well, so today we are going to talk about this quantity, which is rate of change of velocity. We'll talk about acceleration. And this acceleration is defined as rate of change of velocity. So if you remember, in our previous video, we talked about when we have a velocity, a non-uniform motion is there and the velocity is there, which is changing every instant of time or over a period of time it is changing. It's not constant, so it's non-uniform motion. Why it is called? Because the velocity is changing. And this change in velocity that is happening over time, we call this quantity as acceleration. So the change in velocity, so this basically is rate of change in velocity. So this means that you have velocity different and we have a delta time t. So in 1 second, what is that change happening? So this A is equal to rate of change of velocity. So velocity is changing. We have some, suppose we take v as final velocity and we take u as initial velocity, then this is the change v minus u over delta time t. Delta time t is the time interval, and then we get this quantity as acceleration. That is how it is defined. Well, now comes the question, if this rate, that is this rate of change of v with time is constant, then we say that acceleration is constant. So we can have the graph for this. So if you want to make a graph, if we have a here, meter per second square, we'll say if this acceleration is the y-axis, over time we will find the value to be same, and this is a situation of constant acceleration. Well, what would happen if this is not constant? The rate, the velocity change which is happening is not equal, right? For equal amount of time, it is changing. That rate is changing itself. So we'll call that it is a variable situation, variable acceleration is there. Then we are going to average it out. So the average acceleration would be over time interval delta t would be equal to v2 minus v1 over this time interval delta t. So this is what we call average acceleration. So if we want to plot it, suppose we want to plot it and we take velocity here as meter per second, and we want to show that this velocity time graph, so it's not position time graph, it's velocity time graph. It's a velocity time graph. And in this velocity time graph, we want to figure out what would be then, if this is the average acceleration, at any instant of time, any instant, what's going to be the average acceleration. So we'll be getting curve like this, and at any point A, suppose we want to find what is the acceleration here, why it is changing, the rate is changing, it's not uniform. So if it is not uniform, we'll employ the same concept. If you remember, if we draw this AB, it's going to give the average acceleration, right? Now at this instant, if we want to find, we'll then have to take the limit of it. So we will take the limit of this change in, which is the average velocity over time, which is the average acceleration. If we take the limit of this when delta time t tends to 0, when delta time t tends to 0, we take limit of average acceleration, then we are going to get dv by dt. And this is what, so for infinitesimal small time interval t, dt, we take the derivative, we'll take the derivative of the velocity with respect to time, and this is what we'll be getting: instantaneous velocity, acceleration. So this is the concept of instantaneous acceleration, that it is A is equal to dv by dt. We can use this when we have this kind of situation. We have A is equal to dv by dt. Now, having understood these small bit of concepts, we'll move on now to our basic topic, which is kinematic equations. So suppose we have accelerated motion, and that acceleration is uniform, then how we can, from the graph itself, we can figure out what could be the relation between these quantities. So famous three equations of motions. First we'll check with the graph, and then we'll try to use calculus to derive those equations, equation of motions, and then we'll find the relations, and then we can move on to the questions related to this chapter. Well, so suppose we plot a graph here, and we are using the same notations. So we are taking, suppose, the velocity here. It's a velocity time graph in meter per second, suppose. And we are saying that this is initial velocity u. We'll use the same notation, u as initial velocity. And suppose here we have v, which is final velocity. And we have time axis. And we have kinematic equations. We are interested here to find kinematic relations. Kinematic equations for uniformly accelerated motions. So we have u as initial, v as final, and we see that we get this kind of graph. So at this time interval, at this time, suppose, and this is time t, this is delta t. Well, and this is the graph that we get, and this graph, if you see, it's proportional, which means that the slope is constant, right? The slope means from here to here. So from here to here it is v, from here to here it is u. So this is v minus u, and this is delta t. At any point on this line, you would find the slope of velocity time to be same, which means that the slope of this graph is going to give you the slope of velocity time graph gives acceleration. Why? Because this over this is slope, and this over this is what is acceleration. So acceleration is v minus u over t. If delta time t is equal to t, so we get from here at is equal to v minus u. Therefore this v becomes, if you make subject of the equation, it becomes u plus at. So now we are able to get this first equation of motion. All right. Well, if this is a situation from the same graph, if you want to find the second equation and you want to find what is the displacement happening. So these are all vector quantities. This is velocity, this is acceleration. And now we are interested to find what is displacement. So in a velocity time graph, remember, in a velocity time graph, suppose velocity is constant, and at any instant of time, this is what we get at t. This is what we get a figure, right? So now, if you take the area of this, so this is v, and this is time t, right? So if you take the area of this rectangle, this area of this rectangle is displacement, right? Area of rectangle is displacement. Why? Because this displacement is s, suppose. So this displacement is v times t, because this v is equal to, velocity is displacement over time, so therefore displacement. So we know that velocity is displacement over time, so therefore displacement equals v times t. But this v times t is area, right? Area of sorry, it comes area, which is the shaded portion here. This is the shaded portion. Velocity times time. So we can conclude from here. So if the velocity is constant here, the velocity is remaining constant over time, then we get the area. If it is not, if it is different, so one idea is clear, that the graph that this velocity makes with the time axis, the velocity curve makes with the time axis, the graph, the area enclosed here is what is the displacement. So from here we can conclude, suppose now, instead of uniform or constant velocity, if the velocity is changing here like this, from 0 to this, so if this becomes half, again this area is going to give you the displacement in this situation. So from this conclusion, we will employ here, and we'll from the graph try to derive what will be then the area of this enclosed figure. So this is what is the velocity, and this is the area, which is where this curve, this straight line is making with the time axis. If you are able to calculate this area, if you are able to get this area, this would be the displacement. This would be the displacement. So using this concept, we'll move with the equations. So this is triangle and this is rectangle. So this is U. Okay. So area of triangle plus area of rectangle is going to give you displacement. So therefore we can have S in terms of time as this would be equal to area of this, which will be UT plus this, right? So area would be equal to half into base into height. So this will be equal to half into base, which is T, into height, and the height is V minus U. This is what we get for this value we get. Now we know that from here V minus U is AT, right? So we can write this F, therefore S would become UT plus 1 by 2 T times AT. So it is AT squared. So from here we are able to get what is second equation of motion. UT is equal to half AT squared. Okay, now if you want to eliminate t from here and you just want to have a relation with the velocity and the displacement, so we can also find this, right? We can, if you take this trapezium, the area of trapezium is going to be equal to half into the height, which is this, right? This is the height in that situation, and sum of parallel sides. So sum of parallel will be this u, and this complete sum of parallel would be v. So if you add this up, half into this, and the height here, the height is of this trapezium figure is going to be this t. So we can write here, we can eliminate t from here, from this equation as well. So area of trapezium, another way of looking at it is trapezium would be equal to, S would be equal to half into sum of parallel sides, which is u plus v times. Okay, so this is the sum of parallel times this distance, which is time. This is the time delta t. So this is delta t, other time. Well, we also know what is time, so we can write time from that relation. So we can write time is equal to v minus u by a from equation 1. So therefore we get S is equal to, now if you multiply this, this would become a plus b times a minus b. So it becomes 1 by 2a. Here it becomes v square minus u square. So if you bring it here, it becomes v square minus u square equals 2as. So this is the third equation we are getting as equation of motion. So this was the method that we knew already. It's just that a part of recall, we are able to now relate these quantities, and from the graph itself we are able to derive those equations. Now we will be using calculus method to use this to derive the same equations. So you should learn the approach how we use the calculus to get these equations. So take note of this, and then we'll move on to another method using calculus method to get the same equations. All right. So using calculus method, so we'll derive the first equation. We know acceleration is equal to dv by dt. So from here, we can write this dv is equal to a dt. And we use the same notations here. Now if you want to find what is v, right? So we'll be integrating. So the changing thing, the changing element is dv here, and the changing element is dt here. This remains constant, right? Acceleration is constant. So we'll integrate both sides. So we'll write here, integrating. Both sides. We get, we'll take our limit. So initial was u, final is v, and here we have dv equals, a is constant, we'll take out of integral sign. So from time t is equal to 0 to time t is equal to t, and then we have dt here. So if you integrate this, so from here we'll get this v. If you integrate dv, right? So we'll be getting v here, and we write it in this way. V is final, u was initial, a, and here it becomes t, which is t0. So therefore this implies that this becomes, so using the property of definite integral, we get v minus u equals a times t. So which means that v is equal to u plus at. So now we got this same equation as we got earlier, but using this calculus method. Great. So now we are interested in to find what is displacement, right, in terms of this. So we'll use the same notations and we'll now derive the second equation of motion. So we know that acceleration is equal to dv by dt. Okay, acceleration is equal to dv by dt. So can we write this in other form? By other form I mean, can we write this dv by dt as dv over ds times ds over dt? It's the same thing. So we can use this, a could be written as dv over ds by ds over dt. So we want this s actually. So we know that this ds by dt is v, okay? So therefore we can write this dv by dt acceleration as, we can write acceleration as dv over ds times v. We can write this dv over ds times v. Well, now if you make it here, the equation, so suppose we make it this, we'll bring it here, so it becomes a ds is equal to v dv. We get a relation here in this way. And now when we are going to integrate this side, we'll be getting the equation. So if you integrate this, it becomes a where to where from 0 to s ds, and this v dv, right? So we are integrating this, initial was v, final is u, and here we have dv. Well, so from here we get a times s equals, here if you integrate it becomes v squared by 2, right? So this becomes v squared by 2, and here we get v and here we get u. So how do we get this? Integrating both sides. Integrating both sides. So if you integrate both sides, we'll get a times s is equal to 1 by 2. You would pull it out, and this in the bracket we replace this v squared by 2, so it becomes v squared minus u squared. And you bring it here, it becomes 2as equals v squared minus u squared. So we got one equation relation with s, and it is relating with v square and u square. So basically we have derived this equation number 3. We also have one more equation, that is which is relation with t there, with relation with t. So this equation gives you the relation of displacement with velocities, initial and final. And the third equation, or the second equation that we can derive from here. So if I rub this, and now if you want to find in terms of time what is the relation that we get with s, we can use this velocity as ds by dt, right? Very simply we can use this velocity as equal to ds by dt. Therefore this becomes equal to, therefore this ds we want in terms of time, so it becomes v dt. But we know this v is equal to u plus at, right? This v is a function of time, and we can write this is also, it's not independent but it's depending on time. So we have therefore this ds is equal to u plus at dt. Now integrating both sides. Now suppose we take s to be 0 initially, so we can from 0 to s we can write, or if you want to take any specific initial position you can take this, but we are taking say 0 to s, and here also we'll integrate this from 0 to t, so this becomes u plus at. Now when you integrate this separately, so ut and here t squared by 2, so this becomes therefore this becomes s is equal to here ut, and here it's going to be a constant, and this becomes t squared by 2, right? And here we'll use the limits, which is t and 0, so basically it becomes the same thing, t squared by 2, which is equation 2. So s is equal to ut plus half at squared is another equation that we get when we follow these steps using calculus to get those equations, kinematic equations. So take down these steps, very important for your exams, and then we'll be using these concepts that we have learned into how to use in different questions to solve it. Watch the next video for those questions. Thank you.